Hello, in this video we're going to continue seeing proofs of Boolean expression using Boolean algebra property. So if you have those flashcards of all the properties next to you, that will be great. So now here is where we have x plus y naught equal x plus x naught dot y plus xy quantity naught. So it looks like if I start with the right hand side, it will be better. So let's start with that. And I see that quantity not so what I'm looking at is I want y naught and x is here. So all what I'm gonna do, I'm gonna think of what's inside this parentheses and how can we get it to be just y. So when I look, if I use distribution, then x and x naught will cancel out and that will leave me with just y naught. So let me do that. But the first thing is to use commutative law, which is 1b. And then I'm going to use the distribution, which is 3b. And then, as I said, x naught plus x is 1. Because of universal bound. And now I end up with y dot 1, which is 4b, is just y. And then the negation from outside. So then we went from the right hand side to the left hand side. So the next one here, b, as you see, I'm going to try to start with the left hand side. And I'm going to use 2b because first thing I want to write it as x dot y dot z plus y dot z. And then I'm going to use commutative law. And the reason why, because I see y dot z, and my goal is to have y dot z. So let's do that by using distribution. But we first use commutative law, then use the distribution, and then we use the identity. Remember that x dot 1 is just x. And now if I use commutative, that means put y dot z first. Could put brackets here. Then use the distribution, which is 3b. Then I have x plus 1. And again, universal bound, the x plus 1 is just 1. Again, universal bound, x plus 1 is 1, which is y dot z, and that's my goal. Y dot z is what I need. So the next example, we're going to start with the left hand side, because my goal is to get xy plus y, so I don't need any x naught again. So what I could see is that if I use first commutative law, put the y first, yx plus y dot x naught. So what I use is 1b. And then I'm going to use distribution to have x plus x naught, which is 3b. So x plus x naught, that's 1. And then you may think, so what happened to x dot y? Okay, let's see what we could do about that. So, if you remember, 1 will be the universal bound if I have x plus 1. So here I introduce x back using the universal bound. And then if I distribute, that will give me x dot y dot x plus y. And just use the commutative to match exactly what I need, which is a 4b. And this is an interesting trick, even though it feels like you have all x is gone, but you could use universal bound and have x or whatever other variable you may need. So this one here, we have x plus y naught dot z plus x naught dot z dot y. And all of this, where I want to reduce it to just x naught z. Okay, so the first thing I think of, I use the left hand side. And what I'm thinking of is De Morgan. So I get x naught dot y naught dot z plus x naught dot z dot y. And after this one, I'm going to use 2b. because what I'm going to do, I'm just going to move, because the parentheses were here, I'm going to move them here. And then I'm going to use 1b again, just so I could have z dot y naught plus x naught zy. Just I want to have zy for later. So this step can wait for later, but I'll do it now. And now I could use the distribution. You have x naught, and then I will use the distribution again, which is the z out, and then y naught dot y plus y. So I use 3b twice. What we know about y naught dot 1 is just a 1 because of 5a. So here is z, x naught. And then always keep in mind, my goal is x naught dot z, so here is x naught dot z, because z dot 1 using 4b is just z. The next example talks about exclusive OR. Exclusive OR, x exclusive OR y is x y naught plus y x naught. This is by definition. And so right here, what I want to do, I want to just to convince you, let me do the truth table for this exclusive OR using the definition. So here, review this table, or you do it on your own and see. So what does it mean, exclusive OR? So exclusive OR, as we said, is x dot y naught plus y dot x naught. But you see here, when x and y are the same, we have 0. And when x and y are different, we get a 1. So sometimes it's called the bit checking. It's used a lot in computer security when you encrypt and decrypt. So you send some data. Sometimes you want to match these data. Are they exactly the same? So as we said before in Intro to Arithmetics, that the data are sent as, when you click A, it's going to be just 8-bit sent in a wire. And so, for example, I'm going to match, do I have the same A? But if one is 001, for example, and the other one is 0101, so what happens is you do bits checking. So every bit you check, if they are the same, you put a 0, and if they are different, you put a 1. So you have to do something. Usually if you take networking, you will be sending a message again, or your system or your router send a message back saying there is resend data because there was a corruption in the data. So something like that. So what we do, exclusive OR, is that operation that check the bits. We call it bit checking. So this is very important operation used a lot in cybersecurity. So this on the side, let's see now our examples, because our goal here is just to prove things. So let's prove how these are kind of properties for exclusive OR. How do we prove that x exclusive OR y is the same as y exclusive OR x, which is a commutative law? So to do this, by definition, I will start from one side and then use the definition by def. And now what I could say, I use one a. And why is that? Because that will give me y x naught plus x y naught. And again, by definition, this is just y exclusive OR x. Very simple. And the same with the b. So x exclusive OR x equals 0. Again, how you get to 0, I'm going to use the definition, which tells me, x exclusive x dot x naught plus x dot x naught. And I use 5b. This is 0 plus 0. And then if I use 4a, this is 0. For c, you could think about it. 0 exclusive or x is by definition 0 dot x bar or x naught plus x dot 0 naught. This is by definition. And or you could use truth table also and prove this if you want. But we use the Boolean algebra properties here. So here I use 1b, I just moved it around. So this one I know it's a 0. X dot 0 naught, I use universal bound. And as we know, what is 0 naught? Negation of 0 is just a 1. Because 0 naught is a 1. And here 0 and x dot 1 is just x by using 4b. And this is, I could use commutative for the plus, which is 1a, and this is just x because of 4a. So every step has a reason why we move to the next step, and this is how you prove this one. For the last one here where we have, how can we prove that 1 exclusive or x will give me x naught? Truth table or use the properties. So here I'm going to use the properties. Similarly, by definition, we have this. And then I'm going to use commutative property, which is 1b. And then we use 4a because that one is just x naught, that one is x naught plus x dot 1 naught. And after this, we're going to use, again, by definition, 1 naught is a 0. And then dual universal bound, if you want to say. Dual universal bound, that will give me a 0 here. And x naught plus 0, just x naught, that's identity, which is 4a. So this is how we do these proofs by using the Boolean algebra properties. I hope this video is helpful.